Hey everybody, it's Hunter here, and in this video we are going to talk about how to analyze data, particularly in the context of writing your lab reports for this class. So the data analysis quiz is divided into 5 major categories, all shown here, and I'm going to go over each one, the concepts relevant for each one, and then go through some examples. Some of them will be pulled straight from the quiz, so I hope that will be helpful. But if you're following along with the concepts of what I'm will be explaining here, then you'll be able to apply that to the other questions of the same type. And there will be, you'll each have 7 attempts so to take the quiz, and there's no time limit, so there's plenty of opportunity to get a good score on this quiz and start off the session with a A+. So before I begin, I want to emphasize to please reach out for help if you are struggling with this, if some of it is not making sense. Let's say you've taken the quiz 3 or 4 times already and you're still getting the same things wrong every time, then don't just blast through all 7 attempts. Reach out for help and ask us for assistance before you use your final attempts. Okay, so let's talk about units. So it's important to know how to manipulate units and how to represent them in different forms, because you'll need to do that not only for this class and for the lecture class, but also in your future career as an engineer. Units are especially important, and there's an example of what I'm talking about in the frequently asked questions page, by the way, if you'd like to take a look at that. So in general, for the purposes of this class, units are more important than significant figures, by the way, so I want to mention that as well. There are no questions on significant figures in the data analysis quiz, because I'd say units are generally more important because they're closer related to the concepts of what we're trying to teach. And so if you get 20 decimal places on some number that you're calculating just because that's how many decimal places the calculator gave you, feel free to cut it off after 3 or 4 decimal places, and that should be okay. So for units, the example I'm going to use here is the first question from the quiz. And that is on the different ways to represent the unit of electric field. So the conventional way that the concept of electric field is introduced in the lecture is typically by saying you have some test charge in the region of an electric field, and the electric field strength is the force that that test charge experiences divided by the magnitude of that test charge. So you can find the unit of electric field by saying, well, the unit of force is newtons and the unit of charge is coulombs. So therefore the unit of electric field is then newtons per coulomb. But it doesn't stop there. That's not the only way that you can represent the unit of electric field strength. You can also represent it in a different way, or in several different ways. And to convert any units to any other form of units, whether it's an SI or imperial or whatever it is, the trick when you're converting units is to multiply by 1. But you're not going to multiply by 1 in some haphazard way, because that wouldn't end up changing anything. Instead, you're going to multiply by 1 in a way that's useful for you. And it takes some practice to be able to know what is the right way to multiply by 1. So as an example, if I multiply by meters over meters here, then, well, this of course cancels to 1, so I'm not actually changing the units here. But I can represent a newton times a meter as a joule. And then we still have coulombs times meters in the denominator, and you can't really simplify those. By the way, the unit of energy, joules, being newtons times meters because of the definition of work. You have the integral of a force with respect to displacement, so you have unit of newtons times a unit of distance, meters, so then that's a unit of work, which is energy, right? So you can then simplify not coulombs times meters, but you can simplify joules divided by coulombs. So if you haven't seen that in lecture yet, that's okay. the definition of a volt is joules per coulomb, at least in terms of units, right? So you can represent a joule per coulomb as a volt, and you're still left with the meters in the denominator, so therefore we can say that newtons per coulomb is equivalent to a volt per meter. But let's say you are given some weird esoteric looking representation of units. How can you confirm or deny whether or not those units are a valid representation of some other form, right? Well, you can start just by equating them. So let's say if I say volt per meter, I want to know if that's the same thing as saying watt per amp meter, okay? Well, how can I go about figuring that out? Well, first I will try setting them equal, and you might put a question mark over top just to remind yourself that it's not a factual statement, at least you don't know whether or not it is yet. And then you just start canceling things, and you try to end up with the statement 1 equals 1. And if you end up with 1 equals 1, then that is of course a true statement, so that means the statement you started with is also true. So this is the way that you'll test whether or not units are equivalent. If you're not sure exactly what is the right way to multiply by 1 to convert from one to the other, then you can use this method instead to do another check. So you can of course cancel the meters because they're both in the denominator on each side. So you're left with volts equals watts per amp. Well, what is a watt? Well, a watt is a unit of power, which is a rate of energy dissipation or energy absorption, or whatever it is. So it's a joule per unit time, per second. And an amp is the rate of flow of charge, which we'll discuss more in detail further on in the course. And you may have seen it in lecture by now, but the unit of amps you can represent as a coulomb per second. So the unit of charge passing by a given point in a given amount of time. So then you can cancel the seconds, and then you're just left with joules per coulomb, right? And then so we know by definition that a volt is equal to a joule per coulomb, so then we can cancel both of these, and then we end with 1 equals 1. So we end up with a true statement, which means that a volt per meter is the same as a watt per amp meter. So it's kind of a weird representation, but it is factually correct. So then you can try that for the different cases on the other questions, and then if you have any doubts or any clarifications, please feel free to reach out. Okay, so then now let's talk about error analysis. And when do you use percent error, and when do you use percent difference? And by the way, percent error is sometimes called percent discrepancy. I think it depends on who you're talking to, which term they will typically use. I typically will refer to it as percent error, but sometimes people use discrepancy. So if you are doing an experiment and you calculate out some quantity that you're interested in, and you have a theoretical quantity that you can compare it to, then you would want to calculate the percent error between a experimental and theoretical. And so here I'm going to label it, we're talking about error analysis. So if you have an experimental value that you got by taking data, doing your experiment, performing some analysis, and then you also have a corresponding theoretical quantity that you can compare it to, then you're going to use a percent error. And the way you calculate percent error is by taking the difference between the theoretical and experimental quantity and then taking the absolute value of those. So you have experiment minus theoretical, and take absolute value of that, and then you divide by theoretical quantity, and then multiply that by 100%. So to calculate percent difference, you need to have two experimental quantities. You need to have experimental 1 and experimental 2, and you're trying to compare them So if you have two experimental quantities and no necessarily ideal or expected value that you're comparing it to, then you're going to use a percent difference. And the way that you calculate a percent difference is in the numerator, you're basically doing the same thing with the two values. You have experiment 1, experimental value 1, minus experimental value 2. And then you take the absolute value of them, so it doesn't really matter which way you subtract them. And then rather than dividing by the expected value, well, you don't have one in this case. So instead, you're just going to take the average of expected 1 and expected 2. Or experimental 1 and 2, those two values. So the average of those two just being, you add them up and divide by 2, right? And then you multiply all of this by 100% to get your percent difference. So on the subject of error analysis, I also want to mention the concept of precision and how that introduces uncertainty in the calculations that you'll be doing. So anytime you collect data, you're using a measuring device of some kind, whether you're measuring an angle, you're measuring a voltage, or whatever it is, you have to use some sort of device to measure that quantity. And the precision of the measuring device gives you a sort of minimum level of uncertainty for each data point, right? So as an example, let's say I'm measuring a distance, and I'm measuring a distance using a ruler that has increments marked at 1 centimeter spacing. So I have 0, 1, 2, 3, 4, all the way up in units of centimeters. And then I'm measuring something, and I find that the unit comes, or that thing ends up being, about this long, and it might end up, somewhere right around here. Well, you could see by eye that that's a little bit more than 2, but the question is, how do you scientifically rigorously report that measurement, given the measuring device that you used? Well, you would have to say, is it closer to 2.5 or is it closer to 2? So just because of the way I drew it here, I might say it's closer to 2.5, but it'll be debatable between, how it's going if it lands right in the middle. So I would report this value as 2.5 centimeters, essentially. And the reason for that is that the precision of the measuring device is always half of the smallest marked increment that there is. So for another example, if you're using a protractor, and the protractor has markings that are in 10-degree increments, then if you make a measurement, then your measurement can only be as precise as about 5 degrees, because you can't necessarily scientifically rigorously prove that it's slightly more or slightly less. Like, I wouldn't be able to say, oh, I know for a fact just by looking at it by eye that it's 6.3 degrees as opposed to 6.4, right? So that you have to think about what is the precision of the measuring device and then report based on that. And yes, you might know that it's not right exactly at 5 degrees. It might be closer to slightly more than 5 degrees or something like that. But that's okay, because it's going to introduce some uncertainty in your calculations and in your final result. But in your discussion and conclusion, you'll want to make sure to mention where that uncertainty came from. So there can be different places where uncertainty can be introduced in an experiment, but one of those places, and one of the key places for that, is the precision of the measuring device itself. So I also want to mention the couple of ways, the two primary ways that you will see that an uncertainty value is reported, along with its natural value or its actual quantity, right? And that is that you might see it reported as, let's say, if you have a slope, let's say, typically written as m, and it says you get something that's some number plus or minus some other number, Well, if this is just a number and not a percentage, then this is the uncertainty. So it's just the number that comes after the plus minus sign. And by the way, the uncertainty itself also carries, so delta m, being this value here, carries the same units as the slope value itself. So if it's just a number, right, then that number has the value, the uncertainty in the same unit, right? So if you have a measurement that is 2 centimeters plus or minus 0.1, well, it's not plus or minus 0.1 pink elephants, it's plus or minus 0.1 centimeters, right? So the uncertainty itself carries a unit. But that's not the only way that you might see that an uncertainty is reported. You may also see it reported as a percentage. And in that case, let's say I have m equals some value a plus or minus b percent, where b, let's say it's somewhere between like 1% or maybe up to 20%, whatever it is. Well, then how do you find the actual value, the number of what the uncertainty is, not the percentage? Well, in that case, you would say that the uncertainty is equal to basically b percent times the actual value of that quantity, in this case a. So to represent b percent, you want to take the value of b and multiply it by 0.01, right? Meaning that's what percent means. So you're representing that percent as a decimal, and then multiplying by the actual value that is. So for example, if I had like 1.766 plus or minus, let's say, 14%. In that case, then I would say my delta m is equal to 0.14, that's 14% written in decimal form, times 1.766, which would happen to come out to 0.247. So that would be the value of the uncertainty that would also carry the same unit as the value itself. Okay, now moving on to derivatives. The example that I'll use here is actually coming from one of the lab experiments that you will do, and this tends to be a common point of confusion. So I'm going to go through this with you, and you'll see it again later on once we get to Lab 4. You can maybe reference this video if you need to come back and take a look at it. So the problem is that you have, quote, a non-ideal battery with a certain fixed internal resistance, little r, that's delivering power to what we call a load resistor that has a variable resistance. And if all of that sounds like nonsense to you right now, that is perfectly fine. You don't need to understand the circuits component of what we're talking about here, because to solve this problem, all you need to do is know how to take a derivative, basically. But this, everything I just said, the power being delivered to the load is governed by this equation here, and that is epsilon squared times big R, which is the value of the load resistor, divided by little r, which is the internal resistance, plus big R, the load resistance again, squared. So this is sort of the power. This is the power delivered to the load in the case of a DC non-ideal battery, which we'll discuss that more in detail once we get to Lab 4. But what we're going to do for this problem is take a derivative of it. If you're remembering from Calc 1, you might immediately jump to the quotient rule here. I strongly advise you to not use the quotient rule. There may be some cases where the quotient rule is useful, but generally, more often than not, the product rule is going to be more straightforward than using the quotient rule. At least I find for most purposes here. So how do you use the product rule on a quotient, right? It seems kind of like a dumb thing to say, use the product rule for this when it's obviously a quotient. Well, remember, you can represent it as a product. So you can say epsilon squared times r times r plus r now to the minus 2 power, because we flipped it up to the numerator. So this will make it easier to take this derivative than to use the quotient rule here. So if I take the derivative of PL with respect to big R, then that is saying d by dr of all of this, so epsilon squared r times r plus r to the minus 2. And because it's a product here, so I can pull out epsilon squared. It does not have anything to do with the variable big R. So I would end up with an epsilon squared out front, essentially, and then on the inside would be the rest of everything else. So I can write that as, well, it's a product, so I say the derivative of the first one, and then write the second one. So that derivative of r is just 1. Derivative of r with respect to r, right, is just 1. And then you'd write the second term, so r plus r to the minus 2. And then you're going to add the derivative of the second term times the first term. So I'll go ahead and write the first term here, r, and then for the second term we'll pull down the exponent, say minus 2, times r plus r, and then now here's where some students get confused. Remember, when you're using the exponent rule, you are subtracting from the exponent, and in this case you might make the mistake of writing minus 1, because 2 minus 1 is 1, but remember it's already negative. So minus 2 minus 1 makes it minus 3 here. Okay, so then you can simplify this and then represent that in a way that you like, and we're actually going to use this solution or this derivative in Lab 4, but we'll use it in a more practical sense for that purpose at least. So this is an example of a derivative here, but there are a couple of other derivative questions on the quiz. One of them is another problem just like this, so just take the analytical derivative, and then one is where you take the derivative and then plug a number in to get the value of that derivative at a specific point. And if you have any questions on that, feel free to reach out. Okay, so then moving on to the graphical analysis portion of the quiz. When you're plotting something on a graph, you need to decide what to put on the y-axis and what to put on the x-axis. And then from choosing what you put on the y and x-axes, you will get something, in most cases in this class, it's going to end up forming a straight line, and I'll talk about that once we talk about linearization. But the slope of this line is often what is sort of encoding the information that you are trying to calculate. So you need to know the value of the slope, but you also need to know what the unit of the slope is, right? Because it's important to keep track of the units in all steps of your analysis. So how do you know what is the unit on the slope? Well, you might remember from algebra class, right, that the slope is equal to the rise over the run, right? Well, it's not only the rise over the run in terms of numbers, but it's also the rise over the run in terms of units too. So if you put something on the y-axis that has units of, let's say, oh, I don't know, coulombs or something. For some reason you plot charge on the y-axis and you plot distance on the x-axis or something like that. Then the rise is in units of coulombs and the run is in units of meters, so that it's coulombs per meter, which I'm just coming up with random units off the top of my head, but this is the idea, right? So you take the unit of whatever is on the y-axis and you divide it by the unit that's on the x-axis, and that becomes the unit of the slope. So not only can you get the number from that, but also the unit too, which will be important for your analysis. It's also important to know why you are choosing to plot a certain variable on the y-axis as opposed to the x-axis, and why you choose to plot another variable on the x-axis as opposed to on the y-axis. And there's a reason for that. It has to do with causality, right? So it matters for the experimental case of, what is it that you are controlling and what is it that you are measuring, right? You control something, you make a change that affects the measured quantity. So in terms of causality, we would say that what you are controlling is the independent variable, and what that affects is the dependent variable, right? So this is probably just a review for most of you, but it's important for the concept or for the purpose of creating a graph that you know why you're plotting a certain thing on the y or the x-axis. And that is that you want to make sure you're plotting the independent variable on the y-axis and the dependent variable, or on the x-axis, excuse me, and the dependent variable on the y-axis. And again, that has to do with it, causality, right? So it's also important to know why you are choosing to plot certain things in a certain way on the y or x-axis. And that's bringing us to the last general concept for the data analysis quiz, and that is linearization. So linearization is a data analysis tool that allows us to take some relationship between two quantities and plot it using a line to make the data form a straight line. Why do we want it to form a straight line? Well, to put it simply and concisely, is just that it makes the data analysis easier if we can model the data using a line, as opposed to some other weird curvy function that we're not really sure what it may or may not be, or if it's a 1 over x squared relationship, something like that, then it's harder to necessarily see by eye, oh yes, that's definitely a 1 over x as opposed to a 1 over x squared relationship. It's harder to do that. And also you might have more parameters on your model if you're not using a line. When you have a line, there are only two things that can change: the slope and the y-intercept, right? So the idea is that the fewer parameters you have, then the better or easier your data analysis will be. So if it's possible for you to create a line using your data, then you should. So as an example, I'm going to talk about the first linearization question on the quiz, and that is that, let's say you have two objects, M1 and M2. Doesn't really matter what they are, but let's say that they're known values. You put them on a scale and you know what M1 and M2 are, so they're not unknowns. And you know from physics 1 that the force between these objects will be equal to big G, the gravitational constant, times the two masses multiplied together, and then divided by the distance squared. So if I collected a bunch of data on the force versus distance relationship, and I had a table of data that said I measured this much force at each of these different values of distance, then you can try plotting that on a graph if you like. You can say, hey, I manually changed the distance between them, so that makes r the independent variable, and I measured the effect that had on the force, so that makes f the dependent variable. So we would choose to plot the force on the y-axis, and if we chose to plot the distance on the x-axis, then because of this relationship here, then we would expect that this data would form a curve that looks like this. It looks like a 1 over r squared relationship. So that is, of course, not a straight line. So it makes it a little bit more difficult to see by eye, oh, hey, that's definitely a 1 over x or 1 over x squared. So how can we model this as a straight line instead? Well, we can't change anything about or we don't want to change anything about the y-axis, because It is the dependent variable, and we have information on the force already. But we can't plot r on the x-axis because we, of course, get this curve instead of a line. But we can say, hey, what is our final result? What do we want the final result to look like? Well, we want this equation to look like this equation. So y equals mx plus b, where the two parameters in your linear fit model are the slope m and the y-intercept b. So how can you make this the case? Well, we already know that the force is the dependent variable y. So there's this relationship here. That's why we chose to plot f on the y-axis. And we know that x is our independent variable, but in this case, if we plot it as, f versus r, then this is, of course, 1 over r squared. But we can instead write this as g times m1 times m2, and then times 1 over r squared, and then plus 0 in this case. So in this case, 0, our y-intercept should be 0, but by representing it like this, we are calling not the distance between the objects, the independent variable, but rather we're sort of modifying it slightly and saying that 1 over the distance squared between the objects is the new independent variable in the way that we are choosing to plot our data. So that makes 1 over r squared equal to the independent variable, and so we would choose to plot 1 over r squared on the x-axis instead. And if you do that, and you get a force versus 1 over r squared relationship, then your data will form a straight line. And what is the slope on that straight line? Well, we equated y with f, right? We equated y with f, and we equated x with 1 over r squared. So it would make sense then that the slope becomes everything else in the equation that didn't already have a job, right? So the slope becomes then maybe a bad choice to use m for both cases, but fortunately we have the subscripts here. So we would say the slope is equal to then g times m1 times m2. So if you plot the data and you find the slope, then you get some number for this, and you know m1 and m2, then you can divide it out and you can experimentally calculate big G using that. So that is an example of how you would linearize a data set if you're expecting it to behave like this 1 over r squared relationship here. But if it's like a 1 over a distance instead of a 1 over distance squared, well, I'll let you think about that. But if you have any questions on it, then please do reach out for help. So that's all I have to discuss in this video, and I hope it's been helpful for you, and I'll say it one last time, yeah, please do reach out for help if you have any questions. Take care and stay safe. Peace.